Alright, so we're doing graphing exponential functions, and so just these are going to be our basics. You have your standard equation right here, which is y equals a to the x to the power, and that's when a is greater than 1. So an example of this would be y equals 2 to the x, and then that would be a growth equation, which is right here. And when a is greater than 0 but less than 1, an example of this would be y equals 1/3 raised to the x. This would be a decay.
Alright, so here we're going to model a growth exponential function, such as y equals 3 to the x. And here we would plug that in on the y equals as 3 to the x, and we would graph that, showing how it grows at that exponential rate. And then you would have a table that shows you each x point and the corresponding y point, which would also help you graph it on paper and show you where each point is. The domain would be x equals all real numbers. As you can see, it goes both ways at a constant rate. And then range would be y is greater than 0. As you can see, it does not pass the y equals 0 mark. And then the end behavior would be x to the infinity and y to the infinity. And x to negative infinity, y goes to 0. As you can see, the y goes to 0 as x continues to go to negative infinity, and x goes to infinity while y continues to go to infinity right on up. That's your growth exponential function.
So this would be a great example of a decay function, y equals 1/4 raised to the x. And so here's obviously a decay, and of course your table with x and y coordinates. And here we have the domain will be all real numbers, because as the function continues, it'll eventually cover all x values possible. And the range is greater than 0, of course, because it'll never touch 0 because of the asymptote. And end behavior is as x goes to infinity, y will eventually go towards 0 but not touch it, and then as x goes to negative infinity, y will go to infinity.
Here is transformations of the graph. There are 4 ways to transform your graph, and you can either flip it, move it left or right, up or down, and you can change the rate of incline or decline. First, we're going to start off with flip. And for that, you'll have to add a negative onto the front end of the equation, such as this example, y equals negative 2 to the x, which will flip the graph downwards, unlike this graph, which is the opposite. Now, when you're moving it left or right, you will add or subtract a number to the power x, and that will be opposite the sign. For an example, you will have y equals 2 to the x minus 2, and that will move it to the right 2 units. Transformations, again. Here you will start with rising or lowering the graph. And to rise or lower the graph, you have to first add to rise or subtract to lower by a number at the end of the equation. And here we have an example for rising the graph, which would be y equals 2 to the x plus 2. And that will move the graph up 2 points. Over here we have 2 to the x minus 2, and that will lower the graph by 2 points downwards. Very simple. And now we will move to increasing or decreasing the growth or decay. And so, to do that, of course, you have to change the rate at which the function grows or decays. We will start with increasing. And here you must multiply the exponent by the rate at which you want to increase the function, such as here, 5 to the x times 5, and that will cause the graph to move upwards at a much faster rate. Over here, for decreasing, you will divide the exponent by the rate at which you want to decrease the function, and that will cause the graph to much slower move upwards and outwards. Last of all, we're going to be finding the x-intercepts for graphing exponential functions. And to find the x-intercepts, you will look to where the graph crosses the x-axis. the first example is y equals 2 to the x minus 2. And as you can see, it is below the graph, and so when it comes up, it will cross the x-axis. And as you can see here, it is at 1, 0, right there. And over here is another form. Example would be y equals negative 2 to the x plus 2. And that would be where the graph is above the x-axis, going downwards. So you can see it still crosses the x-axis. And that is also at 1, 0.